Hi, this is Eric Funk. I'm one of the co-founders of Mountain Radio LLC, and we've been providing RF design services to clients in the electronics industry since 2003. And then we usually do the RF portion of product designs from scratch. Sometimes we get called on to solve a problem with an existing product that someone else designed. By far the most common single problem that we get called on to solve is poor wireless range in Bluetooth or Wi-Fi enabled designs. And the problem I'll show you how to solve today involved a wearable device which had a Bluetooth range of just about a meter when the actual range should have been at least 10 to 100 times that. When we encounter a problem like this, it is typically due to one of several causes, and maybe you've seen this problem in your own designs. First, you may be starting with a textbook antenna design or a design worked out by someone else, and these designs rarely account for parasitic effects from your circuit board layout or from stray resistance, inductance, or capacitance that exist in real components at RF frequencies. Second, you can now buy a variety of chip antennas off the shelf for common wireless frequencies such as 2.45 gigahertz. These antennas look great on paper, but getting them to work properly requires that the antenna be mounted on a circuit board in a very particular way. Most importantly, though the chips may be on the order of a millimeter square in size, chip antennas typically require a ground counterpoise of around, 10 square centimeters, sometimes greater, in order to work to specification. And often you can do just as well with a good circuit board antenna or a wire antenna at virtually no additional component cost. Plus, just as I mentioned above, the vendor recommended match for these devices cannot account for the details of your layout, including other components located in or near the ground counterpoise. The vendor recommended match for a chip antenna also may not account for the stray resistance, inductance, or capacitance that will exist in the real components that you will be using at RF frequencies. So let's address these issues. If you are designing a wireless device from a single chip solution, that's typical for most applications these days, you'll notice that these devices are usually designed to drive a 50 ohm antenna. For example, if the final stage RF amplification is functioning as a voltage source, then if the real part of the load impedance is larger than 50 ohms, power delivered to the antenna will be lower than rated, and if the load is smaller than 50 ohms, power delivered could be higher than rated, and that can reduce the product lifetime. And not discussed here, if power is delivered through a transmission line to your antenna, the impedance mismatch will cause power to be reflected back into the RF amplifier, possibly shortening the lifetime as well. So in order to optimize the wireless range and maximize the lifetime of the components in the RF amplifier, the goal is to terminate your transmitter output stage with a 50 ohm impedance antenna, and that will allow you to route the antenna via standard 50 ohm transmission line as well. However, real-life antennas will typically have a completely different impedance than 50 ohms at your frequencies of operation. At first glance, it may seem reasonable to place a transformer in line in order to step the real antenna impedance up or down by the factor necessary to get 50 ohms. But there are a few problems with this approach. Foremost is that while an ideal transformer can scale the magnitude of impedance, it does not account for the fact that an antenna will invariably have a reactive component to its impedance. And the real component of the antenna impedance is its resistance, including the effect of radiated power and resistive loss. Without getting too terribly technical, the imaginary component is due to the current and voltage at the antenna terminal getting out of phase with each other due to capacitive or inductive reactance, and that's related to energy storage within the electric and magnetic fields of the antenna. Long story short, you can expect any real-world antenna to have an impedance that's not 50 ohms and to include imaginary components in that impedance as well due to capacitive or inductive reactance. Of course, if the impedance is complex and the source is a real impedance, then we understand that the voltages in the circuit, those will also be complex. Again, without getting too bogged down in technical details, it turns out that at RF frequencies, signals travel in waves as governed by Maxwell's equations, and one way that we can measure the complex impedance of an antenna or any device at RF frequencies is by looking at the reflection coefficient. When a source and load impedance are not exactly matched, only a portion of the source wave is transmitted to the load and the rest is reflected back toward the source. This is embodied in the reflection coefficient, shown as the Greek letter gamma. The ratio of the transmitted voltage wave amplitude and the phase to the reflected wave amplitude and phase is the reflection coefficient, or gamma. Gamma is related to both the source and antenna or load impedance in a very predictable way as governed by Maxwell's equations and shown in the equation at the right. When the source and load are matched, then the reflection coefficient is exactly zero and all the power is of course transmitted to the antenna or the load. The Smith chart is one very effective way for us to visualize the relationship between the antenna impedance and the resulting reflection coefficient. The Smith chart on the right shows the complex reflection coefficient gamma in linear Cartesian coordinates with the real portion on the x-axis and the imaginary portion on the y-axis. Thus, the reflection coefficient is a vector with both real x and imaginary y components. Superimposed onto the plot of reflection coefficient, the chart shows a grid which corresponds to the value of a component that we label as lowercase z. Z is the ratio of antenna or load to source impedance. Now we show the Smith chart on the left. This time it is labeled in terms of Z or impedance. If we take a source impedance of 50 ohms, the center point corresponds to an antenna with a 50 ohm impedance and no reflection. An open circuit corresponds to Z equals infinity. A short has Z equals 0. And as it turns out, while the reflection coefficient scale is linear, the corresponding Z scale, which is shown in fine detail in gray underneath that chart, that's logarithmic in both the x and y axes, and that accounts for the pattern that you see there. Inductive reactance in the load will give us a reading in the upper half of the plot, and capacitive reactance in the load will give us a reading in the lower half. So the reason I've told you about the Smith chart is that it is a particularly useful way to display the results when we measure an antenna's frequency-dependent reflection coefficient with a vector network analyzer. The vector signifies that the measurement is of both real x and imaginary y parts of the reflection coefficient. On a network analyzer, this is commonly known as an S11 measurement. The square of the magnitude of the reflection coefficient will give us the fraction of power inadvertently reflected back toward the source rather than being delivered to the load. So S11, when presented in decibels or as a fraction, is also known as the return loss. When we display the results of an antenna measurement on a Smith chart normalized to a source impedance of 50 ohms, as shown on the left, we can see exactly what antenna impedance our measurement corresponds to. 50 ohms is real. 50 ohms real is right there in the middle. In this example, I plotted the reflection coefficient of a previously matched antenna to 2.45 gigahertz as the frequency is swept from 1.9 to 2.9 gigahertz, and we can see that this antenna is entirely within the capacitive reactance section of the chart between these two frequencies. As shown on the right, we can also plot the magnitude of the reflection coefficient versus frequency. The magnitude is shown on the y-axis with a log scale, read in decibels, versus frequency on the x scale with a linear scale. The center line of the y-axis corresponds to 0 dB or 100% reflection. Note that far from 2.45 gigahertz, the antenna has nearly 0 dB or 100% reflection. However, near 2.45 gigahertz, the reflection coefficient is less than 20 dB or less than 1% of the transmitted power. On both graphs, I've highlighted the better than acceptable reflection coefficient range of 10% or negative 10 dB. Notably on the left, this corresponds to a circle near the center of the graph. It is, of course, not practically possible to get the antenna impedance to be exactly 50 ohms over the band of operation. However, if we can get the antenna to within the acceptable range over the band of operation, we can usually consider our job done. So again, our job is to come up with a network to match an antenna with a non-50 ohm complex impedance to nearly 50 ohms real impedance over our band of operation. Though a transformer may at first sound like a good way to reach this goal, transformers are bulky, they're expensive, and they're lossy. And additionally, transformer core materials can exhibit additional complicated behaviors. Instead of transformers with windings, we can use filters constructed from inductors and capacitors as impedance transformers. These can be designed for very low loss, and when a low loss, low pass filter design is used, we have the added benefit of filtering out high frequency harmonics. This will invariably help with regulatory compliance. So if we're matching at only a single frequency or a small band of frequencies, a filter approach can be an excellent one. L networks are very well suited to the impedance transformation purpose. For example, the top plot shows an example of an L network designed to match 1 kilo ohm to 100 ohms at 100 megahertz. Note the L shape of the topology. This is where the name L network comes from. The parallel component, in this case a capacitor, is used to reduce the impedance of the load. We then carefully choose a series component, in this case an inductor, to cancel out the remaining complex component. As shown below, we can swap the parallel and series components and get an impedance step-up version as well. So what happens when the load isn't purely resistive? If the load includes parallel reactance, we can simply make that reactance a part of the shunt portion of the circuit. Here the required 4.8 picofarad shunt capacitance is constructed from both the 1.2 picofarad internal shunt reactance of the load and the additional reactance from a 3.6 picofarad discrete capacitor. 1.2 picofarads plus 3.6 picofarads gives us 4.8 picofarads. A similar approach can be used if the load includes inductive reactance as shown in the circuit below. We just add the series reactance of the load to the reactance from an external series inductor to get the reactance that we want. The required 477 nanohenries equals 10 nanohenries from the load plus 467 nanohenries from a discrete inductor. There are many ways to do this, but this is just one set of examples. So, how do we trade off the value of capacitance and inductance to get the required step up or step down? There's actually a very simple formula which I'd like to put into a spreadsheet. The formula is based on calculating the Q, or quality factor, of both the shunt and series portions of the matching circuit. By selecting the source and load impedances that we wish to match, a little bit of algebra gives us the series and parallel reactances that we need. This method is outlined by Chris Bowick in his highly recommended book, simply entitled RF Design. You'll find the method on page 66. By working from right to left or left to right, you can design either step-up or step-down networks respectively. Keep in mind that 1 over Q corresponds to fractional bandwidth. A high Q will result in a narrow band match, and a low Q in a more broad band match. There are good reasons for choosing one or the other depending on your application and the bandwidth. For instance, by cascading several smaller impedance steps together, we can get a more broadband match than if we did this in a single step with a single L network. But for now, we're just going to stick to a single L network. So now that we've looked at how the theory works, let's get down to doing the match. In our circuit board layout, we've included a spot for 3 TBD to be determined components in a pie-shaped topology connected to our antenna. As shown in the schematic at the upper right, note the similarity in shape to the Greek letter pi. The antenna that we are matching is a circuit board trace antenna. It's for a proprietary design for a wearable device, so I can't show that to you, but I will show you the matching procedure. The pie-shaped topology will allow us to construct almost any kind of L network that we can think of if we leave either Z1 or Z3 unpopulated. We can also populate all 3 components to get a pi network, and there might be some good reasons to do that having to do with Q and bandwidth. But again, we'll stick to the L network here. So I begin with measuring the antenna impedance without a matching network by placing a 0 ohm shunt resistor in the Z2 spot. I then connect the port, shown here as Zin, up to the vector network analyzer. That's this, and I plot the resulting S11 or reflection coefficient as we scan from 1.9 to 2.9 gigahertz. Note that I placed the circuit board within the enclosure of the final product so that any packaging effects will be included in the measurement. I turned on a marker at 2.45 gigahertz on my vector network analyzer, that's the center of the band, and the marker reads out rather conveniently in impedance. At 2.45 gigahertz, I get an antenna impedance of 1.8 minus J16 ohms. 1.8 ohms of real resistance in series with 16 ohms of capacitive reactance. The J indicates that this is an imaginary or reactive component, and the negative sign indicates that the reactance is capacitive, not inductive. By the way, we use J instead of I to indicate imaginary, since I is used to represent electrical current, so as not to confuse the two. So the measured antenna impedance is well below 50 ohms, so we'll need to choose a filter that performs an impedance step-up function. From the load on the right and working our way left, we place a series inductor to increase the impedance, and then a parallel capacitor to cancel out the remaining parallel reactance. Since the antenna includes some series capacitive reactance, we'll include this when we calculate the value of the discrete inductor that we'll need. Now we use the equation discussed earlier, the one we put in our spreadsheet, to calculate the reactance of component values needed for a 50 ohm match at 2.45 gigahertz. For starters, to get the series reactance required by the formula, we use a series inductor value of 1.6 nanohenries. The reactance of this inductor at 2.45 gigahertz adds to the internal negative reactance of the antenna, giving us the series reactance that we calculated in the formula. So we now populate the series inductor with values that are close to, we populate the series inductor spot on the board with values that are close to the ideal 1.6 nanohenry. Interestingly, we've decided to leave the shunt spot unpopulated while we measure the reflection coefficient. We're looking to get the real portion of the measured resistance as close to 50 ohms as possible, and we'll make measurements to tune out the reactance as an additional step. Using a variety of discrete inductors with values close to 1.6 nanohenries, we actually got closest to a measured 50 ohm real component with a 2.2 nanohenry inductor. Though we didn't get exactly 50 ohms with any standard value components, the 83 ohms that we did get will still place us in the range of about 1% reflecting power, as we shall see. Since real inductors have a frequency-dependent inductance, and there's also residual effects due to the board layout and the product enclosure, we're not surprised to get a somewhat different value than the value predicted by the equations. Also notice that when looking for a real resistive component close to 50 ohms, we're reading our measured impedance on the vector network analyzer as a parallel equivalent, in this case 83 ohms in parallel with 16 ohms of reactance. Many network analyzers will allow you to read out the impedance in this parallel rather than the series form. If yours doesn't, you may convert series to parallel with some straightforward complex number math or look for a calculator online. By putting the measured value in this parallel component form, we can now easily see the value of the parallel component that will be needed to place we'll need to place on the left to give us a pure resistance. That value is negative J 16 ohms to cancel the plus J 16 ohm of measured resistance. So we're now left with 83 ohms in parallel with plus J 16 ohms of reactance. The reactance can now be canceled out by a complementary parallel capacitor with negative J 16 ohms. That component value is calculated as 4 picofarads at 2.45 gigahertz. Again, we placed several standard value capacitors with values near that, and we test the reflection coefficient for each one, and we found that we actually got closest to purely 50 ohms with a value of 2.4 picofarads. So our best match occurs with a 2.2 nanohenry inductor and a 2.4 picofarad capacitor. This is different than the values calculated from the equations, and it's different enough that had we not taken this in a stepwise manner with measurements of the real components at each stage, we wouldn't have ended up with an acceptable match in practice. The results are shown on the Smith chart plot, and the matching network gives us a 50 ohm match in parallel with a much larger residual 340 ohms of reactance. That reactance is in parallel and almost an order of magnitude larger than 50 ohms. Therefore, it does little to offset the performance of a good match. And you can see that marker 1 at 2.45 gigahertz is almost at the 50 ohm center of the Smith chart. The resulting network gives us a reflection coefficient of better than 1% over the entire 2.45 gigahertz band, or in the typical language of antennas, less than negative 10 dB of transmitted power is reflected back from the antenna. At 2.45 gigahertz exactly, the return loss is 20 dB, or less than 0.1% of the power is reflected back. For a wearable consumer device with a tiny antenna, that's more than acceptable. For industrial, military, or high power applications, a return loss of, well, better than negative 15 dB may be required across the entire band of operation. But this match was used in our client's product, and it was mass produced with excellent Bluetooth range. Note that if we instead had opted to use simulation software, we would have had to have a near perfect model for all of the components and a full-blown electromagnetic model of the circuit board and the product enclosure. However, by simply making real measurements on real components in an iterative manner, we had our match completed in a fraction of the time it would have taken us to even set up a simulation. Since the final network was actually measured as it appeared on the circuit board with the product enclosure, our confidence in the match is very high. So I hope you enjoyed this video, and if you did, please subscribe to our channel so that you don't miss what we have coming next. Your thoughts are always welcome in the comments. Thanks for watching.